this video, we see some basic results and bounds for the chromatic number of a graph. Along the way, we'll determine the chromatic number of a graph for a few families of graphs, including bipartite graphs, complete k-partite graphs, and cycles. So let's get started. So one of the most basic bounds we could come up with right away is we never need to use more than n colors to get a proper vertex coloring of the graph, right? Just assign a color to each vertex of the graph, and that would give us a n coloring of G. And so the chromatic number is at most that. As well, we need at least one color for the graph, unless, because it has at least one vertex. Every graph contains at least one vertex. So, so those are two basic bounds. And then here we can actually say that the chromatic number is equal to n if and only if it's a complete graph. So why is that true? So one, it's easy to see that the complete graphs require n colors. So the complete graph Kn requires n colors, right? Because any two vertices are adjacent. And if, so this is an if and only if, right? So clearly that way works. Chi of Kn is, no, that isn't what I wanted to write. Sorry, the chromatic number of Kn is equal to n. So certainly that's true. So we have to show that it has to be. So right, if we have any non-complete graph, then there's at least two vertices in the graph that are not adjacent. And so we could pull out like this, right? So we have some vertices here. Maybe this is adjacent to some vertices, but at least these two vertices are not adjacent to each other. So I don't know, color this one 1 and color this one 2, and then color the rest all distinctly. So give a distinct coloring here. So every vertex receives its own color. So what'll that, no, I don't want to color this one 1 and then 2, so that would be an n coloring, right? Everything would be a different color. So what I actually want to do, since these two are non-adjacent, just color them both 1, right? So we have an independent set of cardinality 2, and so we can color them each 1, and that requires what? So there's n minus 2 vertices here, and so we have, this is a K coloring where K is, what have we used? N minus 2. So what we have here is an n minus 1. What we have here is an n minus 1 coloring of the graph. And so in the case when G is not complete, chromatic number of G is less than or equal to n minus 1. And then, right, the only graph that that have chromatic number 1, this means that every vertex is independent from every other vertex, right? No two vertices can be adjacent in order for me to use one color, right? The whole graph is an independent set. The other name for that is the empty graph on any number of vertices. We'll have chromatic number 1. All right, let's keep moving along. So we can see this as a connection back to the concept of bipartite graphs, and we can also see this as a determination of the family of graphs that are bipartite graphs. So a non-trivial graph is two colorable. It means I can color it with two colors. So this is the same thing as saying that the chromatic number of G is at most 2, if and only if G is bipartite. So these are exactly the bipartite graphs, are the two colorable ones. So why is this true? So let's say I have a 2 coloring. So let's see a 2 coloring of G. And then V1 and V2 are my color classes, and these partition my vertex set. And no two, so any edges, it follows that any edges of G connect a vertex of V1 with a vertex of V2. Right? There's no edges between vertices in V1. There's no edges in no edges between vertices in V2. And so this is exactly what a bipartite graph is. Hence, G is bipartite. So one thing that we get from this is we can sort of think of graph colorings as a generalization of determining if a graph is bipartite or not. Right? This is the idea. And of course, if G is bipartite, right? So pick a bipartite graph. So how about C6 here is bipartite, and we can color it with two colors, right? So this even cycle 1, 2, 1, 2, 1, 2. It's bipartite with partite sets V1, which would be this vertex, and this vertex, and V2, this vertex, this vertex, this vertex, and V2. And so it's bipartite. Another useful property is this hereditary property of graphs, that the chromatic number of the graph is at least the chromatic number of any subgraph. So why is this true? Well, let's write a proof just so you can see an example of actually proving a statement like this. So I want to show that chromatic number of H is at most K, so I want to give a K coloring of H. Right, so given a K coloring of G, show that I have a K coloring of H. So let C be a K coloring of G. Then the vertices of H, subgraph of G, are also K colored. And so we have a K coloring of H. Hence, chromatic number of H is at most the chromatic number of G. Right? Not a whole lot to show there or say. Though this will turn out to be useful, and in fact we can pair this with a result we mentioned at the beginning of this video. Oh, no, sorry. Oh, boy. I gotta find a way to lock those. To get a nice result here. So, or I guess, yeah. So right. So take a look at this graph. Notice again, it has a triangle in it. So these three vertices here in the middle or on the outside all have to be colored distinctly, right? So I could color this 1, 2, 3. I'd have to color that. So I have to use at least that many colors, right? Because any coloring of the supergraph will be a coloring of this one. And so I have to use at least 3 colors here, and then I can go for, can I do better? And it looks like, yeah, in this case, it's possible to do better. And we have a coloring. So the fact that K3 is a subgraph of, let's call this H. The K3 is a, no, that's, I don't want to call it H. H was the name of the subgraph in the theorem. So K3 is a subgraph of G. Here's G. And we know that the chromatic number of K3 is 3. So the chromatic number of G is at least 3. And then here we have a 3 coloring of G. And so that establishes that the chromatic number of G is at most 3. Hence, this is a 3 chromatic graph. So of course, if a graph is just the union of some number of graphs, or alternatively think of this like a graph, a disconnected graph with these components, then, right, so what if we had a graph, I don't know, like this? We just have these components. Maybe I have, I don't know, it doesn't really matter. Maybe I have a C4 over here. So here's my graph G, and it consists of these components, G1, G2, and G3. Well, of course, yeah, the chromatic number of the graph is just the maximum of any of these, because I would require K colors for that one, and then the other ones, well, it's the max of all of them, so I'd be able to give a K coloring of each of those. And so, yeah, clearly it is the maximum of all of these. So that means we can restrict our attention, right, when in our study of the chromatic number of particular graphs. It doesn't really make sense to look at disconnected graphs because their components just turn out to the maximum. And so in order to determine that, we would just study the chromatic numbers of each of the individual components and just take the maximum. So we don't really look at that. And in fact, there's another class of graphs that we really don't need to look at on their own. And this is the two connected graphs. Remember, this is the same as saying that it's non-separable. So remember, non-separable means no cut vertices. It takes at least two vertices to disconnect the graph. So we can also think of these as two connected graphs. And what we can do is, so to illustrate this, is I'm going to pick out the blocks. So I don't know if you remember the blocks. Blocks were, yeah, good thing I put this slide here. Maximal non-separable graph. So I'm just going to draw the blocks. We looked at these at the beginning of the course. This is a block. And then actually these vertices here are also a block. Right, so I look at all the blocks of the graph. And so notice it takes 4 colors to do this one. Right, so I could go maybe 1, 2, 3, 4 for the colors there. And then color the rest of the blocks, right? So this one is going to take the most number of colors. And I can color the rest of the blocks. Since 2 blocks connect at a single vertex of the graph, so any two blocks share only a cut vertex. And what that means is I can color this in such a way, take all the colorings for all of my blocks, and since it only intersects another block at a cut vertex, what it means, so if I color that 4, well, I can take a coloring over here using any, at most 4 colors, and just do a coloring that leaves this vertex 4, right? So I could go from here and just color this, say, 3 and 2. And over here, I could color this, I don't know, 3. And then I can move on to this other block, and I just have to give at least a 4 coloring where this vertex is colored 3, right? And so there's always a way to do that. Given any coloring, I can just pick this as my vertex. Or if you think of this, I can shuffle around. I can just change my color classes, exchange color classes. I'll just say that and sort of explain what I'm doing there. So maybe I color this 1, 2, and 4. Right, and so really, we just need to study the blocks of a graph. In order to determine the chromatic number of a graph, we simply need to look at the blocks. And how does this relate? The idea is that, so with blocks, so let's say blocks B1, B2, B3 up through BK for some K, then the chromatic number of G, again, it's just the maximum of all the chromatic numbers of the blocks, of the individual blocks. So again, we don't really look at chromatic number of separable graphs. We don't really need to, because we should just study the blocks. That is, the two connected graphs. Laggy computer, sorry. And another way to see how these relate, remember that if you take the join of two graphs, right? If you take, let's say, K3, and let's say join this to a K2, what you do is you make all of the possible pairs of vertices between the two graphs. Every vertex here is adjacent to every vertex here. And so one can prove that this is the sum of the chromatic numbers of each part of the join. I'm not going to prove that one. I'm going to leave that up as an exercise to the listener. So finally, let's determine the chromatic number of a infinite family of graphs. So yeah, how about cycles? These don't have a lot of edges. This would be nice to work on. So let's start with C3. Well, it's a triangle, and so it takes, right, it takes three colors. Sorry, C3 takes three colors because it's K3, right? C3 is isomorphic to K3, or they're really the same thing. C4, well, that's bipartite, right? So I can get away with using two colors. And it's not empty, so I need at least two colors. C5, it's not bipartite, right? It has an odd cycle in it. So remember that odd cycle, so G, remember that G is bipartite if and only if G contains no odd cycles. So here's an odd cycle, and so I need to use at least three colors. So if a graph is not bipartite, that means chromatic number of G is at least three. So this one is going to take three colors. 1, 2, 3, 1, 2. 1, 2. And now C6 again, that one's bipartite, so we can color that with two colors, right? And I can go just 1, 2, 3, 1, 2, 1, 2, 1, 2, and I'll get to the very end. So one thing you could do here is, so in order to prove, so what we're seeing here, and I think we have a pretty good argument for this, is that the chromatic number of Cn is 2 if n is even, and 3 if n is odd. And so as a little short proof here, let's say Cn is bipartite and non-empty, right? So bipartite means that chromatic number of G, right? That means it's two colorable, so that means chromatic number of G is at most 2. Non-empty means the chromatic number of G is at least 2, right? The empty graphs are the only ones with chromatic number 1 is at least 2, and so that follows that. So C is bipartite and non-empty if and only if n is even. And so that tells us that the chromatic number of Cn is equal to 2 if n is even. So if n is odd, then what? Cn is not bipartite. So the chromatic number of Cn would be at least 3. And so now we need a 3 coloring of it. So let's say the vertex set of C sub n be, let's give ourselves the cycle. Let's say it's U1, U2, up through UN minus 1, and finally UN. And so give our coloring C of UI. So the coloring of UI is going to be, I'll color it 1 if I is odd. So I'll go 1, 2, 1, 2, 1, 2, but it'll be odd, and so I'll need a third color, 2 if I is even. So when I think about this 1, 2, this is V1, V2, V3, V4, V5 is odd and not equal to UN, right? The last vertex I need to color differently. So then I'll say, oh boy, I'm sorry, I ran out of room here. And then I'll say I'll color it 3. I'm sorry about that. I'll color this vertex UI 3 if N, or if I equals N, right? So that last vertex I'm going to assign 3. So that's not what I did quite here. I would have done 1, 2, 1, 2, and then color that 3 as a way to always do a coloring. And so that shows the chromatic number is at most 3, and so we get that it's actually equal to 3. And there's a proof. All right, as a preview for the next video is theorem 14.9, where we relate back to another parameter of the graph, and in particular, the independence number of the graph. I'll see you there. We'll prove it.